Let's take a look at the section 2.6 worksheet on combinations of functions and composite functions. In this section, one of the things we look at is finding the domain of a function. And if a function doesn't model data or verbal conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. We need to exclude from a function's domain real numbers that cause division by zero and real numbers that result in a square or even root of a negative number. So we'll kind of see that as we go along and look at some of the examples here in this worksheet. So if f and g are two functions, the sum, the difference, the product, and the quotient are also functions whose domains are the set of all real numbers common to the domains of f and g. So essentially, we need to intersect the domains. So the sum of two functions is really just the sum f of x plus g of x. But you may see that written as f plus g of x. The difference function, f minus g of x, is simply f of x minus g of x. The product function, f times g of x, is simply f of x multiplied times g of x. And the quotient function, f divided by g of x, or f over g of x, is simply f of x divided by g of x, provided g of x is not 0. And that's what we said earlier, that we want to exclude from a function's domain real numbers that cause division by 0. So notice how here we're kind of saying that same thing in a different way, that if we have a division of functions, the function that's in the denominator can't be 0. So let's look at an example of finding the domain of the rational function 2 over x squared plus x minus 12. Now notice what I'll need to do here to find my domain is to first factor the denominator, because it's the denominator equaling 0 that can cause me a problem. And this denominator factors into x plus 4 times x minus 3. And essentially, I need x plus 4 times x minus 3 to not equal 0. Well, we've learned about, in the previous class, the zero product principle of equality. Well, for the inequality symbol not equal to, we have that same zero product principle. So we need x plus 4 to not equal 0, and one of the differences between this and the equality zero product principle is that the connecting word here is and. So we need x plus 4 to not equal 0, and we need x minus 3 to not equal 0. So if I add a negative 4 to both sides here, I get x not equal to negative 4. If I add a positive 3 to both sides of this unequal statement, x can't equal 3. So I need both of these to be true. So when I go to find the domain and I write it as an interval, then it's an intersection of intervals. So in other words, I need to intersect x not equal to 4 with x not equal to 3. So that's the set where I leave out -4 and 3. So I go from negative infinity to the smaller of these two numbers, which is -4, and I unite that. So this intersection of all the real numbers that aren't -4 and all the real numbers that aren't 3 is the union of everything less than -4 with everything between -4 and 3 with everything greater than 3. So that's the domain of f of x. And that's what I look for when I am finding the domain of a function that has a variable expression in the denominator. I'm omitting all numbers that make that denominator 0. Here I have a subtraction of functions, and I basically am going to intersect the domain of these functions. So in other words, I want all the numbers that make x squared plus 1 non-zero and x minus 2 non-zero. So I factor x times x plus 1, and I want that non-zero. So that means x can't be 0, and x plus 1 can't be 0. And similarly, x minus 2 can't be 0. And if I simplify these two expressions or of statements, here I need to subtract 1 from both sides of this unequal statement, and here I need to add 2. This is really a type of inequality. So x can't be 0. And x can't be -1, and x can't be 2. So the intersection of these three sets is the union of intervals from -infinity to the smallest of these. So -infinity to -1, union -1 to the second smaller, which is 0, union 0 to the largest value here, which is 2, union 2 to infinity. So notice what happens. If there are 3 numbers that I need to leave out of the domain, that results in 3 plus 1 intervals that are united. So 3 numbers that need to be omitted gives 4 intervals that are united. Notice, so you always get one more interval than you have numbers that you're excluding. When I had 2 numbers that were being excluded, I had 3 intervals that were united to give my domain. All right, when I want to find the product function, f divided by g of x, I simply divide the one function by the other and simplify. And this is going to take you to a topic that was taught in the previous course, because what we have here is a complex fraction, and that's never left as a final answer. So remember, in the complex fraction, which is a fraction over a fraction, you need to rewrite this where your main fraction bar, so notice I'm going to kind of make it a little thicker. Here's my main fraction bar, and it's longer than all the other fraction bars. So this numerator is called a minor fraction, and so is the denominator, 7 over x plus 8. And so the main fraction bar can be replaced, any of the fraction bars can be replaced by division. You just have to make sure you're dividing by the appropriate expression. So I'm dividing by 7 over x plus 8. And remember, when you do fraction division, you invert what you were dividing by and change the division to a multiplication. So this would be the simplification of that. F over g of x simplified is 9x times x plus 8 over 7 times x minus 4. And notice, once I have it written as a product, numerator is multiplied by numerator, denominator is multiplied by denominator. And I can simply leave that in this form. There's no simplification that I can do here. But what I do have to remember, so I was asked to find this function. So here I found it, and I'll just highlight it by putting a box around it. And I need to find the domain. Now remember, there's a couple of things going on. None of these denominators can be 0. So that would mean x can't be 4, and x can't be negative 8. But there's something a little more complicated here, and that is that, and we actually don't have a problem, but in this particular case, 7 over x plus 8 also can't be 0. And it turns out that never is 0, but if it could be, I would have to omit the values that made it 0. So notice 7 over x plus 8 is never 0. So I don't run into any problem because there aren't any x's that make that 0. So if there were any x's that made it 0, those would have to be omitted as well. So the domain of f of x is the other thing we were asked to find. Is the interval from negative infinity to negative 8. Unite it with the interval from negative 8 to 4. Unite it with the interval from 4 to infinity. And that is our domain. here we want to use the graph of these two functions. The red graph is g of x, the blue graph is f of x. We want to use the graph to solve the following. So we want to find f plus g of negative 2. So that's really just, we have to understand that that's just f of negative 2 plus g of negative 2. And those are just the y values on f that correspond to an x of negative 2, and added to the y value on g that corresponds to an x of negative 2. So we have to look at the graph. We go to negative 2, and we see that f is positive 1 when x is negative 2 on the graph of f. So the y that has the x coordinate of negative 2 is 1 on the graph of f. The y that has an x of negative 2 on the graph of g is 3. So this result is 4. 1 plus 3 is 4. We want to do f over g of 4. So let's go to 4, and we see that f is undefined at 4, and g is 0 at 4. So this whole thing on 2 counts is undefined. It's undefined for 2 reasons. So I'll say because f of 4 is undefined. Notice when x, there is no point on f that has an x coordinate of 4. So f of 4 is undefined. No point on x has an x coordinate of 4. And it's also undefined because g of 4 is 0. And we can't divide by 0. So we have 2 reasons that that's not defined. The domain of f plus g is all values, all x values, or the set of all x values, for which f and g are defined. So the domain of f plus g is, now notice g is defined for negative 5 and 5 and all numbers in between. F is defined for negative 4 and positive 3 and all numbers in between. So G is defined for a bigger set of numbers than F, and for every number for which F is defined, G is defined. So this domain then is actually the domain of F, because that is contained within the domain of G. So it is the interval from negative 4 to 3, including negative 4 and 3. So this is an interval. And notice both sets have to be defined in order for the sum to be defined. So it turns out the domain of G contains more x values in the domain of F, and every value in the domain of F is in the domain of G. So the intersection is the smaller set, which is contained in the bigger set. All right, let's find the domain of F over G. Now, notice that's going to have to be the domain. That's going to have to be the domain of, same as the domain of F plus G. So all values for which they are both defined and for which g of x is not 0. And notice g of x is never 0 on the domain of f, which is from -4 to 3. So both sets for the domain of a division, both sets have to be defined. Both sets are defined from -4 to 3, including -4 and 3. And g can't be 0 on the domain of f over g. And notice g is never 0 between -4 and 3. All right, a composite function is basically an operation. It's a function that results when we perform this operation called composition between functions. So f, and this is red, f composed with g, or f of g of x. It's another way you can read it. You can say f of g of x. This does not mean multiplication. It means that I'm going to make g of x the input of f of x. So this is the domain of this is the set of all numbers x in the domain of g, such that g of x is in the domain of f. And here you have a little illustration. Any x that go into this function have to be in the domain of g. So I have to be able to put those into g. Additionally, those g values have to be able to go into f. So you kind of have a little illustration here for that. So let's take a look at this. F of x is 2x squared plus 3. G of x is 4x cubed plus 1. So I want to find f of g of 1. Well, that means I take 1, and I have to be able to put that into g. And whatever g of 1 is, that has to go into the function f. Well, when you put 1 into g, you cube it, and whatever that is, you multiply it by 4, and whatever that is, you then add 1. And that's what you're going to put into f. So this is f of 5. And that, when I put a number into f, I first square it, then I multiply by 2, and then I add 3. So this is 53. All right, let's find g of f of 1. Okay, I added a few more steps for part A there. Let's find g of f of 1. So notice, we're going to notice something here as we find this. So this is g of f of 1. This is g of 2 times 1 squared plus 3, which is g of 2 plus 3, which is g of 5. which is 4 times 5 cubed plus 1. 4 times 125 plus 1. So 500 plus 1 is 501. All right, let's find f of negative 2. So into the function f, we're going to put f of negative 2. So we've got to go into f, and we've got to replace x with negative 2. And whatever that is, we're putting that into f. So this is f of 11. So we need to calculate 2 times 11 squared and then add 3. So this is 2 times 121 plus 3, which is 242 plus 3, which is 245. All right, so that's what f of negative 2 is. Similarly, we want to find g of negative 1. So that's g of negative 1. So we're taking g of 4 times negative 1 cubed. Notice how when I raise a negative number to a power, I have to parenthesize that negative number. And I add 1 in order to write that correctly. So I have g of 4 times negative 1. Negative 1 times negative 1 times negative 1 is negative 1. So negative 4 plus 1 equals g of negative 3. And again, what does g do when you put something into this function? It cubes that something, multiplies it by 4, and adds 1. So I have 4 times negative 27 plus 1. So negative 108 plus 1 is negative 107. All right, so that's how I compute composition of functions. Now let's look at finding a composite function in its domain. Now remember, what has to happen, if I'm going to compute f of g of x has got to be in the domain of g. This orange set is the domain of g. So I have to be able to take what this x is and put it into g. And I'm going to get a g of x. But notice what I'm going to do with g of x. I'm going to take g of x and I'm going to put that into f. So g of x has got to be in the domain of f. And because that's going into f. So notice you may wind up with a much smaller set of values than what the domain of g is and what the domain of f is. That's kind of what these shaded illustrations are. All right, so let's take a look. I want to find the domain of f of g if f is 3 over x minus 5 and g is 2 over x plus 1. So f of g of x, so this is part A, is f of g of x, which is f of 2 over x plus 1. Which tells me to go to the function f, and wherever there's an x, instead of putting an x, I'm going to put 2 over x plus 1. That's what that's actually telling me to do. And so this is f of g of x. And I need to simplify this. This is a complex fraction. And I need to simplify it. And notice that the numerator doesn't contain a fraction, but the denominator does. Oops, that's a 3, not a 2. So here's what I'm going to do. I'm going to look at all my minor fractions. In this case, I only have one minor fraction. And that minor fraction is 2 over x plus 1. When you only have a single minor fraction, you're going to multiply every term in the numerator with the denominator of that minor fraction, and every term in the denominator by the denominator of that minor fraction. So that's what I'm doing here. Another way to think of this is that I'm multiplying the numerator by x plus 1, and I'm multiplying the denominator times x plus 1. And that's important because, as I know I can do with any fraction, I can multiply the numerator and denominator by the same non-zero number. So whatever x plus 1 is, as long as it's not 0, I can multiply the numerator and denominator by that, and I don't change the value of this fraction. So to multiply the numerator by x plus 1 means 3 times x plus 1. To multiply the denominator by x plus 1 means to multiply every term of the denominator by x plus 1. And that's what I'm showing here. So the numerator, I'm going to just, for the moment, I'm going to leave that as 3 times the quantity x plus 1. And the denominator, the whole reason I was doing this was to get rid of this minor fraction in the denominator. So 2 over x plus 1 times x plus 1 is simply 2. And then here I have minus 5. I can multiply in any order, so I can put that 5 first. What you want to avoid at this stage is the temptation to divide out these x plus 1s. You cannot do that because x plus 1 is only multiplied by part of this denominator, not by every... Once you've divided this x plus 1 in the denominator here by this x plus 1, you no longer have an x plus 1 involved here. You simply have a 2. So you have to actually multiply through here. So this is a place where people really have problems. Think about this and look carefully at what's being done here. So I'm going to distribute the product of negative 5 times x plus 1 in this part of the denominator to get minus 5x minus 5. And this equals to 3x plus 3. 2 minus 5 is negative 3 over negative 3 minus 5x. And you might want to write that as 3x plus 3 over negative 5x minus 3. So that's my final result. So notice that the domain of this composition, f has to be defined, g has to be defined, the resulting composition also has to be defined. All right, so in order for f to be defined, x can't be 5. In order for g to be defined, x can't be minus 1. In order for f of g of x to be defined, minus 5x minus 3 can't be 0. Which basically means negative 5x can't be 3. Which means x can't be negative 3/5. I'll divide both sides there by negative 5. So the domain of f of g of x is the interval from negative infinity to negative 1, unite it with the interval from negative 1 to negative 3/5, unite it with the interval from negative 3/5 to 5, unite it with the interval from 5 to infinity. So remember, there were 4 values that I had to omit from the set of real numbers. Automatically, I know that that's going to be a union of 4 intervals. You always get one more interval than number that you have to omit from the set of real numbers. Okay, so in this kind of problem, it's easy to kind of forget. It's easy to just think about what's the domain of f and g and forget about the fact that you cannot have a 0 in this final denominator either. Okay, so here's your composition, f of g of x. We were asked to find that. And then we were also asked to find the domain. So you always kind of really want to get in the habit of looking back at the problem to make sure you've done everything the problem asks you to do. So I also want to find f of f. So I want to find the composite function f of x, and I also want to find its domain. Okay, let's do the B part here. Let's find f of x. So f of x can also be written as f with input f of x, read the same way, f of x. And that basically tells me in the function f, so I'm looking up here at f, in place of f, x in f, I'm going to put f, which is 3 over x minus 5. All right, so obviously x can't be 5 or else f isn't defined. But I also can't have this denominator equaling 5 either. So we can simplify that and then find out what that value is. And remember, in order for us to simplify this, we only have one minor fraction, that's in the denominator. We're going to multiply the numerator and the denominator by x minus 5 over x minus 5. And remember that this would mean, of course, x minus 5 can't be 0, which means x can't be 5. So this results in 3 being multiplied by x minus 5. And I'm going to use colors to highlight this to make sure what this means is clear. So every term needs to get multiplied by x minus 5. I'm just kind of showing. So in the numerator, there's only one term, but in the denominator, there are 2 terms. And both of those terms have to get multiplied by x minus 5. Now notice this term that had an x minus 5 in the denominator divides into my x minus 5. And that's the whole, that term is the reason I was multiplying numerator and denominator by x minus 5. So there I simply have a 3. Here I need to distribute this minus 5. So minus 5 times x is minus 5x. Minus 5 times minus 5 is plus 25. And here in the numerator, I have 3 times x minus 5, or 3x minus 15. So I have 3x minus 5 in the minus 15 in the numerator, and I have minus 5x plus 28 in the denominator. And I would just want to make sure there isn't some common factor that divides into all terms of the numerator that also divides into all terms of the denominator. And there are no such factors. Now notice this equals f of x. So that was one thing I was asked to find. I was also asked to find the domain. So obviously x can't be 5 because that's not in the domain of f. So I obviously need to leave that out. But I also need to make sure this denominator is not 0. So I also need minus 5x plus 28 to not equal 0. Which means 28 cannot equal 5x. Which means 28 over 5 cannot equal 2x. All right, so I have two numbers that I need to leave out of the set of real numbers. So that results in 3 intervals that are united to give this domain. So I have all numbers. Remember, I'm leaving out 5 and 28 over 5. So the smallest of these is 5. 28 over 5 is a little bigger than 5. So I go from negative infinity to 5. And I unite that with the numbers between, I want to go, yeah, that's the smallest, between 5 and 28 over 5. Typically, we don't want to write these as mixed numbers because it gets a little confusing to have mixed numbers. We leave them as improper fractions. They just need to be reduced. So there aren't any factors of 28 that are also factors of 5. And then I go from 28 over 5 to infinity. And typically my math lab will ask you to write integers or fractions. So this is the result here. Okay, so we're going to use the graph to find these, to evaluate these composite functions. All right, so g of f of 1 is g with input f of 1. And this is also read g of f of 1, but I'm kind of trying to explain it as I am writing it there. All right, now here's what I want to point out, and that is that I need to go to 1 on the graph, and I need to find the y value of f when x is 1. And I see that's negative 1. So this is really g of negative 1. F of 1 is the y value of the point on f that has an x coordinate of 1. And that's this point right here. Point 1, negative 1. So this is really g of negative 1. And notice when x is negative 1, g is 3. So that y value on g, when the x is negative 1, that point where x is negative 1 has a y value of 3. So this is 3. All right, let's look at f of g of 1. I'm going to take 1, and I'm going to put it into g. That means I'm going to find the y-coordinate on g of the point whose x-coordinate is 1. And whatever that is, I'm going to put it into f. So let's use the graph to find out what g of 1 is. When x is 1, g is 2. Notice how the y-coordinate of this point is 2. So this is really f of 2. So I'm going to take 2 as an x value and put it into f. And I see the result is negative 3. So f of 2 is negative 3. All right, I want to find f of g of negative 3. So I'm going to take negative 3 And at first it's going to be put into G. And whatever that is, that's going into F. So this is F of, okay, so let's take -3 and let's put it into G. Actually, the two functions are equal at x equal -3. They have a value of 2. And that's neither here nor there that they're equal. The point is G of -3 is 2. So now I'm going to take x equal to 2, put that into F. So I go to 2 on the x-axis. I go to F, and I see that the y value of the point on F that has an x-coordinate of 2, the y value is -3. So f of G of -3 just happens to be -3. That's kind of a fluke. All right, let's find G of f of 4. So I take 4 and I put it as input to F. Whatever that gives is now my input to G. So actually, let's go to the graph and let's find out when x is 4, what is G? And I see that G is 0. Notice that this is the point 4, 0. So f of 4, I'm sorry. I need to go in, I'm sorry, I need to be putting 4 into F, not into G. So notice F isn't defined at 4. So this is G of something undefined. So that's undefined. In order for G of f of 4 to be defined, f of 4 has to be defined. All right, so this is undefined since f of 4 is undefined. All right, and that's our worksheet for section 2.6. Hope you find it helpful.